We're going to begin our journey into calculus. So we'll start off with this thing called the gradient function. Now, we know the function, y equals function x there, and basically what that does, if you're thinking of a graph, is it measures the distance of the graph from the x-axis. That's what the y value is. Well, the gradient function, which we symbolise there with f dash x, then measures how steep the graph is at that x value. So, in other words, the gradient of the curve. Or another way of thinking about it, the rate that distance from the x-axis is changing. Now, that thing, what we call the gradient function, is probably more commonly known as the derivative. To start off with, we can use geometry, and that allows, but it's a little bit restrictive, but we can certainly use it to find the gradient function of lines, because they're quite easy to find the slope of, but also semicircles as well. Let's have a look. So lines, a horizontal line would simply be function x equals a constant. Well, if function x equals a constant, and if you think of the geometry of it, the slope of a horizontal line is 0. Therefore, the gradient function must always be 0. So that's using the geometry to get the answer. And if it's an oblique line at an angle, then it's going to be function x equals mx plus b, and we know the slope of a straight line is m, so therefore the gradient function is m. So straight lines, very easy. Let's have a look at semicircles though. Here's our standard semicircle, square root of r squared minus x squared. Unlike the line, there's not a consistent slope, so depending where you are, the slope's going to change. And for a curve, we always define the slope of a curve to be the slope of the tangent drawn in at that particular point. So all right, let's draw in one at a there and have an x value of x, and then the y value would be whatever function x ends up equaling, so square root of r squared minus x squared. Now the reason we can use geometry to actually find this slope is because we know that the radius is always perpendicular to the tangent. And the slope of the radius is very easy to find. It would be the y value over the x value, rise over run. Well, the y value is going to be function x, and the x value is x, so that would be the slope of OA. So therefore, the slope I want is the negative inverse of that. So minus x on function x, and we can make that even better because we know function x has an equation. So if the function is the square root of r squared minus x squared, then its gradient function would be minus x over the square root of r squared minus x squared. Semicircles, again, using geometry, reasonably easy. But all other graphs, we're going to have a problem. And we can really only estimate using secants. So let's have a look at a quadratic, which of course is a parabola. Here's the most basic one, function x equals x squared. If I wanted to know the slope of the tangent at the point 2, 4, well, I'll choose 2 points either side of that to create a secant. And I'm going to use that to estimate the tangent. So there's 2 points. I've picked 1, 1 and 3, 9. Okay, if I find the slope of that red line, my secant that I've drawn in, and that turns out to be 4. So I'm going to use that as an estimate for the slope of the tangent. Now the accuracy of the answer, of course, is going to totally depend on where I put the 2 points. So I need a good choice of 2 points. That one is correct. The reason is, if I pick any point on the parabola, if I pick it symmetrically, so x plus h, x minus h, which you'll notice I did with that one, I added 1 on and I subtracted 1, then you should get an exact answer. So the slope would be x plus h squared minus x minus h squared over x plus h minus x minus h, and it turns out to be 2x. And that is in fact the gradient function for x squared, 2x. So it gets it exact. But again, it depended on me picking those symmetrically. So with a quadratic, if you always choose symmetrically, you'll get an exact answer. Well, that's fantastic for quadratics. Let's have a look at the hyperbola then. There's the point 2.5. Well, let's use the same idea. I'll pick symmetrically. So I'll use 1 and 3. I can find the slope of that red line. It's minus 1/3. So I'm going to say the estimate for the tangent at 2 is minus 1/3. Now, looking at my diagram, hopefully you can see if I was to draw a tangent there, I don't think it's going to be parallel to that red line. So actually, no, it's not the correct answer. The correct answer is minus 1/4. So choosing symmetrically on this one didn't work. And in fact, you've got another problem with this one too. Like if you've got something that's not continuous, when you pick the 2 points, you make sure it's on the same side of the asymptote. Because imagine I did it this way. Oh, I'm going to put C over there. And I'll use BC as my estimate. Well, you can see it's just terrible. So one, you need an accurate graph. If you've got an accurate graph, then it's probably better to just draw the tangent in and then read off the graph, rise over run. It's probably going to get you a better estimate. Not the best way of doing it, but it is a way of doing it. There's 9A.